Hi everyone, my name is Prakash Vandari. I'm a PhD student at the Department of Civil and Environmental Engineering here at University of Connecticut. I'm working on a TIDC project 1.16 on the development of wireless expansion joint monitoring system for highway bridges under the supervision of Dr. Zhang, Dr. Malla, and Dr. Han. Today I'll be presenting my poster on our research work. When I said the expansion joint, you may have been wondering why do we even care about them and why do we need their monitoring. But the reality is, if you care about your gutters, sticks, your bearings, piers, and abutments, you should worry about expansion joints. Why? Because a poorly performing expansion joint can cause your deck to crack like this, your gutter may buckle like this, your pier cap and abutment cap may crumble because of the water leakage from the expansion joint, and sometimes it can lead to the overall bridge failure like this. So if you want to keep your bridges healthy and long lasting, first thing you need to do is keep your expansion joint healthy. And to keep something healthy, what we do? Well, we monitor their health and then treat accordingly, right? And the monitoring of an expansion joint is just like listening to a person's heartbeat. Just as heartbeat can reveal not only the performance of heart, but also can provide overall assessment of person's health, and expansion joint data can give us an overall health assessment of the bridge. This figure over here illustrate what I mean by this. So this is a typical arrangement of expansion joint in a gutter bridge, and under the action of different kinds of load like one shown here, these gutter moves like this black shape from the red one. And if you see here, these movements are gonna reflected something like this on the expansion joint end. And if we plot those movements, they would look something like this. The overall this big arc maybe because of seasonal temperature change. The small black response may be due to daily temperature variation, and other the smaller peak may be because of daily the traffic variations. So when we measure these expansion joints or monitor these expansion joints, we will have this sort of response data, which essentially would contain information about the gutter health or the overall superstructure health, based on which we can assess it. We can make an overall assessment of the bridge health. So in order to achieve this, we will need two things. First, we will need an expansion joint monitoring system. And second, we will need some sort of methods based on which we can correlate the system measurement with the overall health of breeds. And we are doing these two things on this research project. So this is our final design of the expansion joint monitoring system we want to develop. It consists of three major components: the end node, the gateway node, and the server. At the end node, we have ultrasonic distance sensors, temperature humidity sensors with the microcontrollers, and they measure the joint movement data, the temperature, and other environmental factors from the testbed bridge. And since they stay in the expansion joint, they can have multiple end node if the bridge has multiple expansion joints. The gateway node is basically the microcomputer which will receive data from the in node using a special type of communication system, 6-dish, and then upload those over the internet. The virtual cloud server, which we are using Amazon Web Service, Elastic Cloud Computing server, and that server is going to take those data from the internet, and finally it will display over the website. And all these components would cost basically less than this one concrete block. And due to its low cost, wireless communication ability, and low power requirement, this system can be used for long-term monitoring of expansion joint, and we can monitor the expansion joint in real time using this system. The reliability of this system is tested by comparing its measurement with conventional sensors like LVDT and temperature humidity meters in terms of their sensing capability and the communication lag. In terms of sensing capability, the ultrasonic sensing component of our system performs almost comparable with the conventional LVDT sensor you can see here. And the temperature and humidity sensors in our system also has a comparable measurement with the conventional temperature humidity meter. Also, the communication efficiency of these systems were measured in terms of time lag between the data measurement and data reception into the website. So we tested this lag at 0.1 hertz of sampling rate, and we found that was insignificant. The developed system has been deployed in an in-service bridge in Connecticut for the monitoring of expansion joint from 15th of May to 6th of July for about a 2 month. And during this monitoring campaign, the ultrasonic distance sensors were placed strategically into the expansion joint so that we can measure the longitudinal deformation as well as the rotation of the gutter, and a digital temperature humidity sensors were used to measure the gutter temperature and the atmospheric humidity. All these sensor measurements were communicated over the system, and finally they were collected through the website, and a database is created. These are some of the data taken from the website. This is the gutter temperature during the testing period, and these are expansion joint gap measurement at the gutter level. If you remember, the expansion joint response are almost similar to anticipated pattern we discussed in the first slide. And to further validate these results, we have developed a 3D finite element model in NGS Mechanical, and we compared those results. To validate the field response measured, we analyzed the finite element model for 1 degree Fahrenheit temperature rise with two extreme idealization of pinned elastomeric bearing at these two ends. This is the deformed shape of bridge due to uniform temperature rise of 1 degree Fahrenheit when the bearing are considered fixed, perfectly fixed. This is the linear fit of the axial deformation and temperature of field measurement, and it shows a negative slope of 0.0035 inch of joint closing per degree temperature rise, which means gutter expanded 0.0035 inch per degree rise in temperature. So these on the right are the comparison of the field measurement and two extreme support condition idealization from finite element analysis. So the first one is considering the elastomeric with no fixity along the axial direction. We got 0.006 inch of movement, and when we consider it a fixed with full fixity, we got 0.002 inch, and our field measurement lies in between those two extreme values. This shows a field monitoring and expansion joint results in good agreement, and model updating and data fusion for overall health assessment of bridge is still going on. Conclude, we have successfully developed a wireless bridge expansion joint monitoring system which can send the bridge response data to our office, and the expansion joint response measured by this system contains the response due to temperature change, traffic, and other type of movement which would be exploited to assess overall health of bridge. Finally, I would like to acknowledge funding agencies, TIDC, CTDOT, and all my lab mates who helped me in this project. Thank you.